Hi everyone, and welcome to week 4 of iolite's Python for LA-ICP-MS course. If you've been following along every week, congratulations on making it this far. We're nearly halfway done. If you're just jumping in, you may want to review the content from earlier weeks to get up to speed. In this week's lesson, you'll learn everything you need to create your first QAQC module for iolite using Python. To get started, let's have a look at the things we'll talk about today. First, we'll talk briefly about why QAQC is a good idea and why you might want to write your own QAQC modules for iolite. Then, we'll review what an iolite QAQC module actually is and how they work. In preparation for this week's example and assignment, we'll have a short primer on some Python features that you may not have encountered yet. We will also do an introduction to using Qt to make user interfaces and Matplotlib to make plots. Then, I'll live code an example QAQC module, and finally, we'll discuss this week's assignment. So, why do QAQC? Generally, QAQC is done to provide confidence in the results obtained, and a framework by which problems can be identified. Although we are talking about QAQC and iolite today, it is worth reminding everyone that QAQC is not something that can be done after the measurements are made unless there has been adequate planning. For example, have backgrounds and secondary reference materials been analyzed? Have they been analyzed at a suitable frequency? And so on. These decisions must be made before measurements are made and the data are processed in iolite. There are a number of reasons to use the QAQC functionality of iolite. Ultimately, the reason to use QAQC modules in iolite is to be sure that your results are good before you export them and use them in subsequent calculations or interpretations. It can also be handy to have some QAQC data when it comes to submitting papers for review. Second, iolite allows you to calculate your results in a variety of ways using different settings. Using a QAQC module is a quick way to check whether the changes have made an improvement or not. Another reason is that iolite has built-in support for automation via processing templates. These templates can import your data, create selections, run checks via scripts and data reduction schemes, and ultimately export your data. But they can also run QAQC modules. By incorporating one or more of these modules into your processing template, you can not only process your data quickly, but also with confidence. Finally, iolite includes some common QAQC modules, but many people have unique analytical setups and/or measurements they're making. By doing QAQC in iolite with some custom modules and your knowledge, you can be sure things are performing as you expect, even for the most obscure configurations. Next, let's talk about what iolite's QAQC modules are in a little more detail. First, let me show you where you can find QAQC modules in iolite and what they look like. The QAQC area of iolite can be found by clicking on this QAQC icon on the left-hand side. When you click on that, you will be presented with a list of the available QAQC modules next to that. And if a module has this little symbol here in line, that means that it's a Python-based module. We have buttons at the top of the list here to create a new QAQC module, a button to import an existing Python script from somewhere that isn't in your path, and a button to edit a Python-based QAQC module. Now I have the Gabbros dataset open, and so if I go to secondary check, you can see that the name, authors, and description are presented down here. And if I double click on that, a sub-window pops up. Now along the top of the sub-window we have a button for settings, run, and export. If I click the settings button, I will see a small dialog to configure this QAQC module. And now I believe in this dataset we have BCR2G as a secondary standard, so if I use that, and I'll just leave the other settings the same, you can see that now a report here has been filled out. So we have the name of the material we selected at the top, followed by a plot and a table of the different channels, the elements, what was measured, what the accepted value is, and so on. So this content here is all HTML. So that's, the same type of language that many web pages are written in. If we wanted to save this out, we could click this export button and we could save it directly as HTML, or we could save it as a PDF. When you export your data in the Export tab, you can click an option to include QAQC results, and that'll include the plots and tables. Now, in processing templates, you can see QAQC, or you can add QAQC modules as well, and you can do that by going to Add, and then Run QAQC module, giving that action a name, and then specifying which module you want to run and configuring it here. So that's QAQC in iolite 4. So, to recap, a QAQC module's output is an HTML report containing text, images, and tables. They also have a status upon completion that can be success, warning, alert, or an error. There are two basic things a QAQC module must do. It must provide a settings dialog to configure the module, and it must update the HTML of the report. We'll get into the specifics of this shortly. Note that you can run QAQC modules individually, as I've just demonstrated a moment ago, but they are even more powerful when used in a processing template. When it comes to actually writing the Python code for a QAQC module, here are the things we need to consider. First, we need to include the metadata at the top. Most of this is self-explanatory, but it is worth a reminder that the type must be QAQC, and the metadata syntax with the number sign and the slash is strict. The script only needs to define two functions, one to update the report and one to create the settings widget. These functions take no arguments, as shown here. Finally, in your script, you can expect to find the usual data and iolog objects. This time, however, we also get a QAQC object. I've listed here most of the QAQC functions you'll need to use. If we follow the QAQC dot with success, success with warnings, success with alerts, or error, that is known as a status and can be fed into the finished signal. Clear report will clear the HTML of the report. Push HTML and push image will append things to the HTML report. Note that the argument to push image is a QImage. We'll learn later how to convert a Matplotlib to a QImage for use in a report. Then we'll have a series of functions that deal with the settings. Their usage should become more clear as we go through our example later today. To effectively create QAQC modules for iolite, we need to learn about a few more Python features and packages, and even a bit of HTML. A few Python features we'll use today that I don't think were covered by the Python for Everybody course are shown here. First, we have what is known as a list comprehension. These allow you to effectively combine a for loop and even if statements into one concise line of code. So, in the example I've shown here, I have a list of selections that I've retrieved from iolite called cells. Then, in the square brackets, I'm getting the results value for each selection and the uranium-238 channel, and I'm doing this for each selection in our list of selections. The equivalent code using a for loop might look like this. Here is another example, list comprehension. This time, I'm starting with a list of channel objects retrieved from iolite, and I am making a new list with the channel names for each channel in our original list of channels if the element property is lead. The equivalent code using a for loop and if statement might look like this. The next feature we're going to look at is called f-strings. This is just a way to neatly embed the contents of some variable or expression right inside of a string. And we do that by prepending the string with an f, and then enclosing the variable or expression in curly brackets. I have two examples shown here. In the first instance, the first value in our list of values is inserted into the string. And in the second, we're doing a bit of math inside the curly brackets. Lastly, I'd like to mention lambdas. A lambda allows you to define a one-expression function that takes any number of arguments. These can be especially handy when connected to Qaqc signals, as you'll see later. So in this example I have here, I'm creating a lambda that takes an argument x and adds 1 to it. If we assign that to +1, we can then use +1 like a normal function. Since our QAQC reports are essentially HTML documents, let's have a look at some basic HTML syntax. The report itself is displayed as a QTextEdit widget, and so supports a limited set of HTML tags. You can find the specific tags at the URL listed here. Many HTML tags wrap whatever you want them to operate on, so a common syntax is shown here where we have our opening tag, which is enclosed in angular brackets, followed by our content, in this case stuff, and our closing tag, which is similar to our opening tag but also has a slash at the start. Some of the useful tags supported by QTextEdit are listed here, where we have heading, bold, and italic tags to style text, line breaks and horizontal lines to section things off. Simple lists and tables are also supported. Here the OL stands for ordered list and LI stands for list item. And for the table, TR stands for table row and TD stands for table data. Most likely you will not be creating tables manually, however, as Python and Pandas contain some helper functions for this purpose. Next, let's talk about user interfaces with Qt or Qt. User interfaces are composed of many objects called widgets. Everything you see in this example dialog here is a widget. There are many more widgets available. Here is that URL where you can see the basic widget classes, including things like checkboxes, combo boxes, labels, line edits, and so on. There's then a series of advanced widgets, and that includes things like lists, tables, and tree views, as well as calendar views. There are organizer widget classes, and that includes things like the group boxes and splitters and tab widgets. There's a whole series of graphics view classes, and you likely won't be using those in Python plugins, but these are the types of things that were used in iolite's imaging features. There's a bunch of model view classes. Now these can be useful if you want to make a custom model to be used in a list, table, or tree view. And then we have the main window and related classes. This includes things like QMainWindow and QMenu, QToolbar. And then some widget appearance and style related classes, which we can probably skip over, but I do want to point out the layout classes. So these are used to position widgets within a window. Now, I also want to point out while we're looking at this documentation that if I were to come to one of these widgets, if I click on that, it will bring me to the documentation for that widget. And now if I come down, I'll see all of the public functions of that widget, which will be available in Python. And you can see that when you construct a QCombo box, it takes this argument of a parent, which we'll talk about a little bit more. But this tells you all of the different ways that you can add some information to the widget or get its current state. And then if you come down a little bit further, you'll also see a section about its signals. Now, these will be emitted when the state of a widget changes. So if I were to come down to this one here for the QCombo box that's called text activated, and I click on that, we'll see that this signal is sent when the user chooses an item in the combo box. And it's also going to emit what the text is of the selected item. Note that the documentation on the Qt website is mostly about using Qt from C++ rather than Python. So things will not match up exactly, but generally the object functions and their arguments will be very similar, if not the same. Coming back to this dialog, you can see here a QLabel, a QCombo box, a QCheckbox, a QPush button, a QRadio button, a QGroup box, a QTab widget, a QTable view, a QProgress bar, and even a few more things. To get widgets into a user interface, they are related in a couple of ways. The first is that each widget has a so-called parent widget, unless it is a top-level window. You won't need to worry about this too much in Python plugins for iolite, but it is good to be aware of it, as you'll see in the Qt documentation that all widgets have a parent argument in their constructor. Having these parent-child relationships for Q objects or Q widgets is important when it comes to memory management. For example, if the top-level window is deleted, all of the widgets inside of it should also be deleted, and this is kept track of via these relationships. The next way they're related is using layouts. Layouts help to organize the widgets into a window in a particular way that will respond when the window is resized. Qt comes with several layouts, including a QForm layout, a QVBox layout, which lays out widgets vertically, and a QHBox layout, which lays out widgets horizontally. Every widget has a layout, and layouts can be nested. Obviously, this can get pretty complicated, but for the simple settings dialogues we will be making today, it shouldn't be too overwhelming. Once we have some widgets created and laid out, they all generally have functions to set and retrieve their current state. The exact syntax will vary by widget, so please refer to the Qt documentation for the control you're interested in using. Lastly, we need to be able to respond to a change in our user interface's state. To do that, we can connect to a signal of the widget. For example, in our code, we could write button.clicked.connect and then specify the function to call when our button is clicked. Again, the specific signal names and their arguments will vary by widget, so you'll need to check with the Qt documentation. To illustrate some of these concepts, let's now have a quick demo. Now let's have a look at some of these concepts in action. To start, let's create a blank Q widget. So to do that, we need to import from iolite.qtgui Q widget. So we can create a blank widget by typing w equals Q widget, open and close parentheses, and then we can resize that widget to something a little bit larger, and then we can show the widget just like that. So now if we click run, we have this blank window that's 500 by 500 pixels in size. Okay, so we can close that. Now, suppose we wanted to create a Q label. So we would add Q label to our list of imports. And we could do L equals Q label. And we can specify what the label text should be right here. So this is my label. And I'm not going to give this a parent right now. So we can do L.resize and L.show. Now if I click run, I get two windows. So one is my blank widget and the other is my label widget. Now, because neither one of them has a parent, they're both top-level windows, so that means that they have window decorations and so on. Now, if I create another widget, L2 is a Q label, and this time I'm going to put some tags here to make it a little bit larger. These are just HTML tags. And this time I am going to give it a parent, which is the second argument here. So I'm going to put a W there. So the widget, the blank widget, will be the parent of L2. So now, if I click run, I've got my, so first I'm going to have to show this. So now if I click run, I've got L here. So this is my label, and my second one. So this is my widget that's containing my second label. Now if I went on and created a third label, actually I'll just copy and paste this. This is my third label. I'll call it L3. Again with the parent of W, I'll click run. And now we've got L, which is just the plain label. And now we've got our widget with L2 and L3, but because they're not in a layout, they just overlap each other. So you can see there's just a big kind of mess here. So what we need to do now is bring in a layout. So we'll use a QVBox layout. So we can get rid of these, I think. And we'll do w.setLayout QVBox layout and w.layout.addWidget L, w.layout.addWidget L2, w.layout.addWidget L3, and then I'll do w.show. Get rid of that one. Now you can see that all three labels end up in our one widget. Even the one without a parent, it gets the parent once it's added to that layout on the widget, on the blank widget. So now all three labels belong to the blank widget that we created at the start, and they're all in this layout, and you can see that as I resize the window, the labels move around to accommodate the space. Okay, so let's add a few more different widgets. So now we'll bring in QComboBox. So we'll do CB equals QComboBox. We'll give it the parent of W, and we will add items. We'll do LA-ICP-MS. So this is a list of strings. And now we'll do w.layout.addWidget CB. When I run that now, you can see I've got this combo box with the different options here. Now at the moment, we haven't told it what to do when we select a different item. So if we want to respond to that, we can use signals. So we can do cb.textActivated, which is a signal of a QComboBox, and we can then on that call connect. Now here we can specify a function or a lambda, and for simplicity here I'm just going to do a lambda for now. Basically just an inline function, so that this is telling it when we activate a different text entry in the combo box, it's going to print the name of it. So if I go run, now when I select an item, you can see over here in the Python console that it's printing the item that's been selected. Okay, so now we'll add one more widget, and we'll do a QPush button. So we'll do pb equals QPush button, telling it that we want the widget to be the parent. We'll do pushButton.setText, and we're going to call this close window. Then we'll do pb.clicked, so that's a signal of a QPush button. So the clicked signal, which will happen when somebody clicks the button. Then we'll connect, and in here we'll do a lambda, but we'll do w.close. This will close our widget. And then we can't forget to do w.layout add widget pb. Now if we run it, we've got our button at the bottom, close window, and if we click it, the window closes. Now, just want to show one more thing here, and that is to do with memory management. So if I do w.destroyed connect, that's another signal that will be called when the widget is actually destroyed and that memory is freed. So we'll do .connect, and we'll say lambda print widget destroyed. So when I run it and I click close window, you'll see nothing happened there. So it didn't actually destroy it, it just closed it, which is effectively just hiding it. So if we actually want the widget to be destroyed and free up that memory, we can import from Qt core, import Qt, and then down here we can say w.setAttribute qt wa_delete on close. That tells the widget to delete itself when it's closed. So if I click run now, so I click close window, you see widget destroyed. Now I could also do and now when I click it, you'll see that it's actually freeing up the memory of all these controls. Okay, so that's great. The next thing that we could do is turn this into a subclass of QWidget so that we can actually reuse this bit of code. If this was a widget that we might want to use in more than one spot, then we could turn it into a reusable class. So we'll do that now. So we can, to do that, we can do class myWidget, and then in parentheses we can tell it which object it's a subclass of, which is going to be QWidget. Then we have to define a function that's this init function, and it'll take self and parent. We'll set the default parent to be none. Now we also need to call the initializer on the subclass or on the parent class. But now we can basically just indent this and change as needed. So anywhere that it used to say W will now say self. So far so good. We probably don't need to do that. Okay, and now down here we can do something like this to create our widget. Let's see if I missed anything. Run. There. And close, and things are destroyed. So the nice thing here now is that we could easily create another one. Now we've got two of them. And then another nice thing we could do is actually create other functions on our class. So we could do, for example, something like this. Create another function there to process whatever is activated by our combo box, and then we can replace this bit of code here with self.process. And now, when we change this, it is actually calling that function. Okay, so I think that should help to make those concepts a little bit more clear, and now we will get to use it in our settings widget for our QAQC module later. The last package I want to introduce before we get to our live coding example is Matplotlib. Matplotlib is probably the most widely used Python plotting package. I think it is best to dive right into a demo to see how it all works, but I'd also like to point out a couple of resources on the Matplotlib website, shown here. In particular, the example section. Okay, let's have a quick look at how to use Matplotlib. So to start, normally we would do import matplotlib.pyplot as plot. However, because we're not sure what other plugins are using Matplotlib, it is good practice to start with import Matplotlib and then do matplotlib.use and then select which backend you want to use for Matplotlib. So if you were using it in a user interface, if you wanted to use a Matplotlib widget in an interface, you could use the Qt5 AGG backend. Or if you just want to be able to save a figure, you could just use the AGG backend. I think for this, we'll use the Qt5 AGG. We want to make sure we set it to that because it's possible that a different plugin may have set it to just AGG before it ran. Okay, so we would do that and then import this pyplot as PLT. That's sort of the customary thing to do. And now our first step will be to generate some data. So we'll also import numpy as np. And then we'll do, so we'll generate some x data by doing np.arange. We'll use 10 data points, and then we can do y equals x squared, and we could do a y error equal to, I guess, np.random.rand. So we'll generate 10 random numbers between 0 and 1, but because that might be a little small, we'll also multiply that by 5. Okay, so if I ran this now and brought out this panel, I would see that I have, let's clear that, run it again. Okay, you'd see that I have, so for x, the numbers 0 to 9, for y, 0 to 81, and random values for the y error. Okay, so if we just wanted to plot that, we could do plt dot, so we'll say plot the data. So we'll do plt dot plot, and we can do x, y, and then we'll also give it a style. So that should make a red dashed line with circle markers, I believe, and we'll give it a label. So the label could be my data, and then we'll do plot.show. Okay, so as you can see, I've got a red dashed line with circle markers plotted here. So I could resize that and so on. Okay, so there's a variety of things we can do now, but one thing that you're going to have to get into the habit of before plotting any data is doing plot.clear. So CLF, I believe, stands for clear figure, and so that gets rid of anything that was on the PLT, this pyplot object, before running your script. Otherwise, things will persist between runs. So we could do plot.legend, run it. Now you can see we've got this legend shown. We can also add X label. We can add a Y label. And you can see that information showing up there. We could also specify X limits, so we could go from -1 to 11. And we could also do Y limits. We could go from to 100. And you can see that all taking effect here. You can also see that the legend repositioned itself for some reason. It seemed to think that that was a good spot to put it. I think it must prefer to go in the upper right, because clearly there's more space in the upper left. But anyways. Okay, so we could also change this from being just a normal plot to being error bars. So I believe that's error bar, and then we would do X, Y, and actually let's pull up the documentation for that and just have a quick look. So if I pull that up here, you can see, so it takes X and then Y, and then the Y error and X error, and then format. So there's many different arguments here, many of which are optional. So sometimes it's helpful to pull up the documentation and have a quick look, or to look at an example. Okay, so I think it's like this. I can do that, and then I'm going to put in a bunch of other codes. So that'll give us, I believe, the circle markers. We can do change the size of the error bar caps. We can set a color, and we'll set a label again so that it shows up in our legend. So let's try that. Great. So now you can see the error bars plotted. I'm just going to see what happens if I don't know, maybe I won't do that. Because next thing, or later on, we'll add a fit to this. Okay, so we've got the error bars plotted now. Yeah, I think let's add a fit. So we've already got NumPy, and it has some rudimentary fitting functions in it. So we'll just use that. So I think we'll move that show command down here, and now here we'll do fit equals np.polyfit. I think it takes x, y, and then the degree of the polynomial, which we know is going to be 2, and then the weights. So we're going to say weights is 1 divided by the error squared. This is actually just going to return the coefficients of the fit polynomial, so we can also use this other function np.poly1d to turn that into a function that we can use. So now we would be able to do something like this, I think. So if we now did that, and then fit of x, and we can give this a something like that. Let's see if that works. Yeah, so now you can see that we've created a polynomial fit, and that's this dashed red line here. Okay, so one more thing that we could do, or that we might want to do at some point, is add rectangles and things like that, different shapes onto the plot to highlight a different region, something like that. So we're going to add a rectangle, and the way that we can do that is from matplotlib.patches import rectangle. And now adding a rectangle is simply doing rect equals rectangle, yeah. And now the first argument is the lower left xy's coordinates. So since we've set limits of -1 and -10, we'll do -1, -10. And then we will do a width is the next parameter, I believe. So we'll do a width of, say, 3 and a height of 110, so it covers the whole range. And then we can do, I think we can also specify color with FC. That's the face color. You can also do different edge colors and things like that. So then we would need to do GCA, which gets the axes of the plot, and then we can do add patch and add that rect. And then we can try to run it. yeah, so now we've got this yellow rectangle going from our lower left and covering 3 in X and the full range in Y. Okay, so now the next thing we'll go through is how to save that. So if you wanted to just save that as a PDF or something like that, it's as easy as just doing plt.savefig, and then you can specify a path. And you can save that as a high quality PDF even. So let me just pull that up and show it. Right, so there's a nice high quality PDF of our figure. But something we're going to need to be able to do later is get this into a Q image so that we can use it in our QAQC module. So the way that we do that is a little bit tricky, so I'm just going to show you here. So we're going to need to import from Qt GUI, we're going to bring in QImage, and we'll also bring in QLabel and QPixMap at the same time so that we can demonstrate using the QImage in a Qt widget. So we'll get rid of this for now. We can even get rid of this, I think. And we will now, we need to do a couple things, I guess. So if we're not actually going to show the plot, we need to make sure that we do GCF, which gets the figure object, and then get the canvas of that and draw it. And then we need to get the width and the height of our figure. And then we can create a Q image by using the memory of our canvas. So we're going to do plot.gcf.canvas.buffer RGBA width height, and then we need to specify the format that the data are in. So the format, as you might have guessed from this RGBA, is RGBA and then 888. That. So we should be able to run that now, I think, but nothing shows up, of course, because we're not showing a plot, we're just creating an image. We should be able to open this up and see that we do indeed have a Q image there. So one thing we could do to see that that worked would be to do, I think it's image.save, I think. So let's try that. We'll do, and then we can just do image.say PNG. Is that the right syntax? It appears to be. So if I bring that up, you can see there's a picture there. That's the PNG we just saved. So we know that it's creating the Q image properly. We could also make a label, and then we could do set the pixmap for that label. I think by doing qpixmap.fromImage and showing that. Right, so now this isn't using Matplotlib, this is using the Q image that we generated. So this is a Q label with a qpixmap that we created from the Q image. Okay, so I think that that's everything that we should need to know about Matplotlib to get going on our QAQC module. Now we're equipped with everything we need to write today's example QAQC module. My plan for this module is shown here. Basically, I'd like to write a group uncertainty checker that determines if the %RSD of a group's selections meets some criteria. In particular, I want it to be a warning if the %RSD is greater than some value when using all of the selections, and an error if it is still greater than that value when using outlier rejection. For this module, we'll need a few settings. First, we'll need to be able to specify which group to check, we will also need to specify which channels to check. We need a setting for the maximum RSD to allow, and finally a setting for the z-score to use for outliers. The output of our module should contain a plot showing all of the selections and highlighting the outliers. It should also show a table with the values color-coded to easily see the exact values of the outliers. And as I was saying, we want to have a different finishing status depending on the %RSD and our settings. Now let's get coding. Okay, so let's create the QAQC module that I just described. To get started, I'm going to click on the QAQC tab here, and then click the New button. This will bring up a small dialog just asking you for some of the metadata. So the name of the plugin, I'm going to call it Group Uncertainty. The description could be something like checks the uncertainty of group stats, something like that, and I'll put my name as the author, and I'll say to open. Okay, so now got that open here. I'll just get things sized. Right, blow this up a bit so you can see it. Okay, so I can fill in a bit more of the information here, or just verify that what I've entered is correct. We have no reference for this. I could probably get rid of that first line. I tend to clean up these comments from the template, and we'll get rid of some of these things that we're not going to need for this one. We will use a QCombo box. We will use QImage. We're also going to use that channels combo box. We're also going to use something called a Q double validator, I believe it's called. Okay, and we've still got so we've already got our import statements for Matplotlib. We're not going to use that in this example. We'll come back to the update function. Actually, for now, we could even just get rid of everything that's in this template here, and we'll come back to that in a minute. So to start, we'll do the settings widget. So which we can probably adapt from the template here. So what I'm going to do is we are going to change this group line edit to be a group combo box, and we'll change that to QCombo box with the parent widget. We can then paste that on here. Name, that's all fine. Okay, so that'll be our group combo box. We will change this channel line edit into a channel combo box, and that'll be our channels combo box that we imported from iolite.ui. So we can replace those as well. And now, so we've created, the group combo box here, and then we're setting so this should be set current text, I believe, for a combo box. So we're setting the text to be whatever's in the settings as group name, and then we're telling it that when we have text changed, which we could probably change to text activated, which is a bit more specific. That text change is whenever the text is changed, whether that's through the user interface or programmatically. Text activated only is triggered if they do something through the user interface. So now when the text is changed in the user interface, we're going to set the group name. So we can do that by calling qaqc.setSetting. where the first parameter is the name of the setting and the second parameter is the setting value. And then we can just call form layout.addRow. Then this first part will be the label, and the second part is the control that we're adding to that row. So similarly here, but now that we have to change this, so we need to do a couple things. So first of all, we want to be able to set it so that we can select more than one channel if we want to. And then we'll also do, so we don't need to do that here, we'll do that later. This is going to be now, instead of text changed, it will be channels changed. What did I want to do here? Nothing, I don't think. So now we're going to do channel, let's see, we'll call this channels, and then we have to do this a bit differently. We'll do channel cb.channels string dot split, because this channel string is a semicolon delimited list of the channel names that are selected. I'll be sure to put that there. Okay, now this we can call max line edit. So this will be max RSD is the value we're going to use there. Max RSD. Notice that, so for this line edit here, when we get the text changed signal and we connect that up to a lambda here, this X value is actually going to be a string, but we want to store it as a float. So we can do that just by wrapping this bit in float. And call that maximum RSD. And then we're also going to put in an option to set a z-score value that we'll use for outlier rejection. So we'll do z-score line edit. Oops. Z-score cutoff, we'll call that. That'll be our setting name. Z-score cutoff. That's going to be a percent. Right. So you can set the parents on all these. It's not necessary, but it's good practice. Okay, so let's switch to iolite and have a look at this. Okay, so we have our first error. Let's investigate. Right, okay, so what this is telling us is that our settings do not yet have a parameter called max RSD. So we can bring this back up, and the way that we'll deal with that is we'll move all of our things where we're setting parameters down into a separate block down here, so that if any of them fail, we'll just let that happen and we'll pass. This one as well. Okay, let's save that and try that. Okay, so we have a little settings dialog here now that pops up. We can get rid of the... okay, so we don't have any groups in our thing yet. And we do have channels. So one thing we forgot to do was add in the channel or the group options that we have. So we'll come back to our code. And up here for the group combo box, we'll do group cb.add items. And we can do data.selection group names. Right, and now let's try that. Right, so now we have our selection group names are in that combo box, and we can select any of the channels. I should also point out that I'm using the Gabbros dataset that we often use. Right, so we haven't actually told it what we want our default values to be. So let's do that next, because you can see right now that when we come to this, we have no value for the maximum RSD or the z-scores cutoff. So let's set some default values. We can do that just by fixing this part here. I'm also going to wrap this in a try except thing, because if we were to come to this without having any selection groups or something like that, we would also get an error. So we'll do group name, channels, could just be that, data, selection group names. Now we have max RSD, and our default for that could say be 10. And our z-score cutoff default could be 2. And now I think when we come here, yes, so now we have our default values put in here for the maximum percent RSD and the z-score cutoff. All right, so we have our settings widget created just like that. I think that that pretty much has all the features that we want. Let's just verify now that things are being stored correctly. So the first thing we'll do up here in our update function is to get the settings and print them out. So we can say settings equals qaqc.settings. We don't necessarily need to do this. We could have just used qaqc.settings everywhere, but this just simplifies things and makes it look a little bit tidier. Another thing that we're going to do right at the start of any update is we're going to call qaqc.clear report. And I also like to do qaqc.push HTML, and then I will give it a bit of a title here, so I'll call it uncertainty check. Okay, and now we can go for key in settings, and we can do qaqc.push HTML, and now we'll use an F string, and we'll do bold, and we'll do our key, and we'll undo that bold tag, and then we'll do settings key over here, and then we'll do a BR, which is a line break. So let's have a look at what that's doing now. So if we come here, you can see, oh, we still have this old setting that we put in some defaults for before. Let me just see if we, I'm not sure, if we close that. Okay, that's a fresh start, I think. So if we set that and those, yeah, there we go. So now we can see our settings here where we've got channels is a list of channel names. Actually, it's a tuple, that's fine. Group name, max RSD, and z-score cutoff. So we know we're getting our settings correctly from our settings widget. Now we just need to process those settings to create, to do some calculations and create figures and tables and so on. So we'll go back to our code, and let's see, what's the next thing we could do? I guess we need to use those settings to get all the relevant things. So we could do, let's also do this in a try, just in case our settings are incorrect. So we can do our group is data.selection group, and then we can do settings. We can get the group name from the settings, and we can do channels. And here I'm going to use a list comprehension to get the actual time series data objects instead of just the channel names. So I'll go data.timeseries C for C in settings, and we'll get the channels. And then we also need the max RSD, and that's just settings max RSD. And we need the z-score cutoff. And that'll just be settings z-score cutoff. And then we'll finish that try statement with an accept pass. We may want to, in this case, so if there's a problem with our settings and we can't get one of these things, we should probably push a HTML message into our report to just say that there was a problem. So we could do something like cannot run with these settings. Okay. So I guess the next thing to do would be to get the data. So we could do df, we can use our data.frame function to get a data frame from iolite, and we'll get our group.selections will be the selections we'll want. We'll get our selection names, and then we can just do channels, and we will get our mean and our int2se. I think that should be enough information. So if we wanted to plot this, we're going to need some x values. So we could do x equals np.arange for the length of the data frame. And then we could go for channel in channels and create a plot for each channel. So our y values will be the channel.name with the mean. We'll do that in an f string, so that should get us our y data. And then the RSD should just be 100, or the percent RSD should be 100 times y dot std for the standard deviation divided by y dot mean. And then we could get the y error similar to the y by doing df and then an f string of channel dot name with int2se. Now we could calculate the z-scores using something in SciPy. So we would need to do from scipy.stats import z-score. Yeah, that's the one. We'll also need numpy, so we might as well do that. Import numpy as np. So now we could do z-scores equals numpy. We'll get the absolute value of the z-scores, and then it's just z-score of the y value. So now we have our z-scores there as well. And now that'll allow us to do our outlier rejection. So to get the y values that are all within some z-score, we could do something like y and then index it by z-scores less than z-score cutoff. So we could do that, and then do the same thing. We'll divide that by y z-scores less than z-score cutoff dot mean, and we'll call this rsd underscore OR for outlier rejection, and we'll just do 100 times that to get it as percent. Okay, so those I think are that's everything that we need to have calculated. Now we could start creating the plot. So remembering that we should usually start by doing a clear figure to get rid of it, whatever was there before. And then we'll do the data as error bars. So we'll do plot.errorbar, give it the x, y, and then y error equals y error. And then we could give it some format, so we can make it so it's circle markers, and we should also, or at least I prefer it with a cap, so we'll give it a cap size as well. Okay, let's see. So In order to get this into one of those QAQC reports, we need to be able to turn it into a Q image. So, if you remember from earlier, the way that we do that is by making sure that we draw it first. So we'll do plot.gcf.canvas.draw, and then we can do width and height. We can get the width and height by gcf.canvas.getWidth height, I believe, and then we can do image equals QImage. We'll have to do bytes plot.gcf.canvas.buffer RGBA width height, and then we also need to specify the format here. So that's going to be QImage.format underscore RGBA 8888, I believe. So now we can do QAQC.push image and give it that image. And now let's just see if all of that stuff that we wrote works. So we'll come back to iolite and click run. Okay, so it didn't run. And that's because I've got a typo in my script here. Or at least that's one of the problems. So we'll go back to the code, and I missed a bracket here. So let's fix that first, and then we'll see. Run. Okay, now I've got an extra bracket at the end, it looks like. And run. Okay, there we go. So we have our selection number on the x-axis versus our selected channel on the y-axis, and we have the error bars plotted, so that's looking good. Let's go back to our code and try to refactor this a bit. So we can, one thing I like to do is actually copy out some of this stuff and put it in a separate function, so that'll tidy it up a bit. So we could say push plot, and we'll just dump all of that in here. Now here we could say push plot. We can also make this look a little bit nicer, so we could do plot.ylabel could be our channel.name. We could do the x label as selection number. We could do a title to show what our RSDs actually were. So we'll do %RSD equals, and now I'm going to do a special thing after the value here to tell it what level of precision I want. So I'm going to do the variable name RSD and then a colon and then .1f, and that'll tell it to do it with one decimal point. And then I'll do the same for the outlier rejected version. Okay, so let's have a look at that and make sure that we didn't mess anything up. All right, so we've got our axis labels now, and you can see the title with the RSD. Okay, this is looking good. Let's clear this, just run it, no errors, no messages. Okay, so another thing that I like to do for a plot like this is to make it a slightly different shape. This is totally optional, obviously, but I'm going to do fig size equals something a little bit flatter, maybe a 7×4. Okay, that's fine. Right. So another thing that we could do is a plot that shows which data points have been kicked out by the outlier rejection. So to do that, we could do plt.plot, and now we'll index the x values by z scores greater than z score cutoff. And we'll do the same for the y values. So y z scores greater than z score cutoff. And we'll give that a, I guess, a red x. And we'll also increase the marker size. I think we can do marker size equals something like 10. Let's have a look at that. Okay, we don't have any outliers here, of course, so let's change our settings. Okay, so you can see now that there is a red X on this one, but it's behind the data point, so we can change that by adding another argument here called zorder, I think, and we'll set that to something a bit higher. Right, so now the X is on front. Okay, so the next thing we need to do is to keep track of whether or not these RSDs are greater than our cutoff that we've specified in the settings, or the maximum percent RSD that we've set in the settings. So we can come back to our code, and we'll create a couple of variables just to keep track of things. So we'll do RSD greater than max, and we'll start with it equal to false. Rejection greater than max equals false. And then we'll add a little something into our loop here that just checks if the RSD OR, or ORSD, is greater than max RSD, which is the parameter that we've got from our settings. So if it's greater, then we'll say RSD greater than max equals true. And we'll do if RSD OR is greater than max RSD, then RSD OR greater than max equals true. Now, what that allows us to do is come down here, and at the end of our update, we can do if RSD OR is greater than the max, then we'll do qaqc.finished, and we'll finish with the code error. And then we can do an else if RSD is greater than max, then we'll do qaqc.finished with a status of success with warnings. And otherwise, we'll do qaqc finished with success. So let's go back and check that. So if we run it, so you can see now that this qaqc module has passed with a warning. That's what it says in this little pop-up down here, and that's because the total RSD is greater than 10, but with outlier rejection it's less than 10. So if I set that to, set the max RSD to 1, then the qaqc module has not passed, and if I set it to 20, then it's just passed. So that's really handy if you wanted to use something like this in a processing template, because you can halt the template on an error and so on. Okay, so we're most of the way there already. We're just going to do one more thing, and that is to add a table to this. So Pandas comes with a really handy way to do that. Basically, we can take our data frame and just do qaqc.push.html. Then we can do dataframe.style.render. So let's see what that did. Okay, so now we've got a table here at the bottom that's got our index, and then our selection name, and then the values that we pulled out with that data.frame command. Now, we can do some things to make this a little bit nicer that are built into Pandas. So we'll come back here and we can add in, so first of all we can do a hide, we can add in a hide index. So if I do that and I come back, that'll get rid of that big index there. We can also add in, let's see, we could add in a background gradient. So if I add in background gradient like that, I think that'll color it for us. Yeah, so that way it shows up which ones are low and high just based on the color. I think that's just about everything that we were planning to implement here, so that's it. The last thing to discuss is this week's assignment. In case you hadn't already guessed, the assignment is to write your first QA/QC module, and I have a couple ideas listed here. The first is to write a module that checks if the uncertainty of each selection in a group is less than a user-specified value, and warns if just one is missed, and errors if all miss. Remember that you can get the uncertainty from a result object, and you can get a result object using the data.result function. The second idea is to write a module that checks if the LOD of the selections in a group is less than a user-specified value, and warns if just one is missed, and errors if all missed. Remember again that the LOD can be retrieved from a result object. Of course, you can also write a QA/QC module using your own idea. We do recommend that you get in touch with us first to be sure that you're trying to do is possible and achievable in the 1-week time period. If you do not have your own data to work with, you can use one of these example datasets that we provide. And remember, please do not get frustrated. If you are stuck, send a message on the forum and we are happy to help. That is all for this week. See you next week when we'll be talking about data reduction schemes.